All right, welcome everyone. I'm Alessandro and Anton is here with me to present today. And today we're going to speak about how LLVM can help us to make it easier to add support for new architectures to QEMU, which is a kind of well-known emulator. But first of all, let's spend a couple of words on us. We both work at Revenge, which is a company that's building a decompiler that is both based on QEMU and LLVM. So we have quite some expertise in this field, but we also do some consultancy on compilers and emulators. All right, let's try to get a quick overview of today's presentation. First, we'll introduce why we wanted to do this project. And then we'll briefly introduce QEMU and its inner working. And then we'll present our two efforts to automate as much as possible the process of adding support for a new architecture to QEMU. Then there will be a brief demo, and then we'll wrap it up. Okay. Let's start with our initial goal, or why did we get into this project? Well, we needed to write an emulator for the Qualcomm Hexagon DSP, which needed to be both fast and hopefully open source, because we like open source. Hexagon is a pretty interesting architecture. It's a VLIW architecture, which means that you have these instruction packets that basically run up to four instructions in parallel. And you have more than 2,000 of such instructions. Some of them are pretty sophisticated and are well suited for basically digital signal processing purposes. And for instance, here you can see a single packet that can basically implement the inner loop of the FFT algorithm. But today we're not here to speak about the challenges introduced by the VLIW architecture for implementing an emulator. We already spoke about that at KVM Forum 2019, and I refer you to that talk if you're interested in that. Okay, let's try to zoom out a bit and let's think about emulators. They're kind of easy to write if you think about them in a naive way. First of all, you need to design a CPU state, which you can imagine as a struct that basically has a field for each general purpose register, floating point register, CPU flags, and things like that. And then you write an emulation loop. This emulation loop starts with fetching the code that you want to execute. Then you decode the instruction in that, let's say, row bytes, and then you extract the operands, fetching them from the CPU state. Then you actually perform the core of the instruction. For instance, here we're considering an addition. And then if it produces a result, you have to update the CPU state. And that's it. Just rinse and repeat. All right, and basically the core of an instruction can be implemented as a simple C function, right? You take in the arguments, say 2 registers, and then you return the result. And okay, we have our emulator, and we can run it. And then you run it, yeah, it's slow. And there are 2 main reasons, let's say, why this interpreter-alike approach is kind of slow. And first of all, it's due to the large overhead for each instruction. You have to perform a function call, set up arguments, and things like that. But mainly, maybe more importantly, every time you need to access the CPU state, you basically need to perform a memory access. And this can introduce a very significant overhead. So yeah, on a second thought, emulators are not that easy to write. So what do you usually end up doing? Basically, you end up having an optimizing JIT compiler that basically is able to optimize multiple instructions in a single basic block in a shot. And so you can imagine that you can align the behavior of each instruction into a single basic block, and you can perform, let's say, cross-instructions optimizations. For instance, you can forward the result of an instruction to its user that might be in the next instruction without having to go through the CPU state, which means memory. So everything remains in a register, and it's very efficient. This kind of JIT are called in the emulation lingo dynamic binary translator, and guess what? QEMU is a dynamic binary translator. Internally, QEMU is pretty much similar to a compiler. It features an IR, whose instructions are called tiny code instructions. But unlike typical compilers, its front ends do not handle high-level languages, but basically assembly for a specific architecture that you want to support. And basically, QEMU takes the raw code, translates it into its own IR, and then you have a regular backend that produces code for the host architecture you want to run your emulator on. So let's look at this IR from a perspective as an IR. Let's say a tiny code is an IR. First of all, it's not in SSA form, but on the other hand, it features 3 types of variables. Global variables that basically are mapped to portions of the CPU state. Then you have local temporaries, which are basically local variables whose scope is the whole function. And then you have regular temporaries whose scope is just a basic block. It's important to stress that each tiny code instruction does one thing and one thing only. So the addition does not touch the CPU flags or anything like that. It just does one thing, the addition. Okay, let's see an example. For instance, here we have an ARM instruction that performs a load from FP-8 and stores the result into R3. And you can see that here on the right, we are materializing the constants -8 into the TMP variable in the TMP1, which is a local variable. And then we're adding -8 to the global variable FP, which represents the frame pointer, and storing the result into TMP2. Then, from this address that we computed, we perform a QEMU-LD, which basically lets you access the emulated address space, and we store the result into R3. You can also, obviously, have control flow in tiny code. For instance, here we can see the translation of a conditional jump instruction where you either jump at 0x2000 or you fall through to 0x1006. And in tiny code, you basically have a conditional branch instruction which compares TMP1 and TMP2. And if the comparison is successful, you jump to the label L1 that you can see basically bounded through instruction below. So the set label instruction sets the position of the label. And then basically, depending on whether this conditional branch is taken or not, you set the global variable PC to 0x1006 or to 0x2000, and then you do exit-TV, which basically brings you back to the emulation loop. Okay, let's see, how can we create tiny code? Well, in a tiny code, or when you are writing a TCG, a tiny code generator, you basically do something similar to when you use an IR builder in LLVM. So, but on the other hand, we have these C functions that are called TCG gen, name of the opcode and size of its operands, that basically emit tinycode.ir into the translation block, which in a QEMU lingo is basically equivalent to an LLVM function. It's important to stress that the tiny code, you just have two data types, 32 and 64 bits integers. So if before we add an addition, a simple C function, now on the right, you can see that we have TCG, so the tiny code generator that takes in input 3 TCGVs, which are basically reference to tiny code variables, and we just emit an addition between the reg A and reg B variables and emit the result into the variable ret. Okay, but overall, this is still not very easy, right? Because for instance, here there's the C implementation of an instruction that performs some vector operation, and it's pretty long. And if you want to generate the tiny code, if you want to write a generator of tiny code that behaves the same way, you have to write quite a lot of code. It's long. It's pretty long. And since this is tedious, we wanted to automate as much as we could. And this is what the rest of the talk is about.
So exactly as Ale just said, we now want to start to automatically generate the tiny code. And now I will start by briefly going over our first attempt to do so, which starts with C pseudocode. Now, the C pseudocode might look something like this. And I should mention, in this case, we have automatically generated all of this pseudocode from the Hexagon architecture library, which is why it looks the way it looks. So it is very Hexagon specific. So for instance, you would infer size information and type information from just the naming of the variables in this case. But anyway, we take these C pseudo functions and we feed them through a flex and Bison parser. And on the other hand, on the other end, I should say, we spit out TCG code. Now, this TCG code, as you can see, is pretty similar to the ad example that Ale mentioned earlier. And there are a few differences. So we start out by creating a temporary variable. Then we assign the result of the addition between the two inputs to this temporary variable. Then we move the temporary to our destination register, RDB, and then we free the temporary. So in TCG, you also have to explicitly free stuff like in C. So this is something that will come up a bit later. Now, I'll briefly want to summarize the results of our first attempt here, which is, well, on the positive side, we were able to generate TCG code for around 1,500 instructions, which is really, really good. However, as I mentioned, both the input to the parser and the parser itself is heavily tailored to the Hexagon. And this is not good because we want to create a more generalized tool. So what are we to do? Well, why not just use C code instead? And if we want to take C code instead of the pseudo C code, then why not use Clang? And this brings us to the second attempt, which parses LLVM IR and then goes from that to TCG code. So instead of having our Flex and Bison parser as we previously had, we start with C functions, we feed them through Clang, end up with LLVM IR, and the LLVM IR is then fed through our IR to IR translator, and we get tiny code or TCG code rather in the end. Now there are two main advantages here to working with LLVM IR. Firstly, we're able to perform lots of essentially optimizations, so we can transform the code and also write analysis passes to get some information out of it. And this is something that was not possible previously at all with our first attempts. And secondly, translating an IR to another IR is also a lot simpler, since the mapping is often one-to-one. It's not always one-to-one, but often. So to work with LLVM IR, we need to use LLVM. So the question is, well, what do we do now? And here we considered two main approaches. Firstly, a regular LLVM backend, as you would write for any other architecture. And then we considered a simple backend, which would implement as a pass over the IR, which just spits out the tiny code. Now, there are a few pros and cons to consider. So going with the regular backend approach, we would get a few things for free, such as liveness analysis and instruction selection. And this is very nice, very pleasant, easy to work with. And this is then, of course, stuff that we would need to do ourselves if we were to write our backend as a simple pass. Now, on the other hand, for a regular backend, there is a lot of boilerplate code to write. And in our case, we do not have a clear instruction format either. We want to emit TCG code, which is essentially just C code. So we need to emit strings to a file. And for these reasons, it was a lot simpler to just go with a simple pass-based backend. So that is what we went for. Now, I briefly want to kind of open up our translator here and show you the passes that it consists of. So we start out by feeding our LLVM IR through inst combine and merge return before we go into a pass that removes phi nodes. And we need to remove phi nodes because the output TCG code is not in SSA form. So we do not have things such as phi nodes and similar. So we need to remove them. Then we go into a liveness analysis pass, and I will briefly touch on why this is important in a little bit. And then we have our last kind of backend pass that goes over the IR and spits out the TCG code. Now let's consider a simple add example again. So this time we start with C functions. And this C function here is also automatically generated, which is why it looks a bit stranger than our previous example. Now we feed it through Clang, and we end up with LLVM IR. And in the LLVM IR, we have a function which takes two arguments, RSV and RTD, performs the addition, and then returns the result of the addition. Now, mapping this to TCG code, we end up with pretty much exactly the same TCG example, only with a few variable names changed. Now, mapping LLVM IR to TCG code isn't always as straightforward as it is with this add example. And I want to cover one such challenge, which has to do with variable lifetimes. Now, in LLVM IR, here I've made a bit of a mock example, but so we create a variable %1 at the top of the function called myInst, or the variable is called %1. Yeah. Then we do some stuff. We eventually branch to a label called BB, which is a second basic block. Then we do some more stuff, and we eventually return. Now, when we want to map this code to TCG, there are a few things to consider. We need to, oh yes, of course. So the lifetime of %1 is in this case the entire function, which is indicated by this orange bar. However, in TCG, we can either create a variable as a TCG temp using TCG temp new, and this variable would have the lifetime of a single basic block, so up until the first branching instruction. We could have also created it as a local temporary using TCG temp local, and this variable would have instead had the lifetime of the entire function, so across multiple basic blocks. And in TCG, we also need to explicitly free our variables. So we need to insert free statements, something like this. Now, when going from LLVM IR to TCG, what do we want? Well, we want to firstly choose the correct type for each variable, so the type with the smallest possible scope, and then we want to free them as soon as possible. And this is important to help QEMU in optimizing the TCG code we generate. And the solution to these problems was the liveness analysis pass, which I talked about earlier. Now, when we're using LLVM, so we asked ourselves, well, what more can we do? And we started thinking about the auto vectorizer. So in LLVM, we have vector instructions such as a vectorized add, which you can see here, which performs an addition of 8 bytes simultaneously. Now we can map this directly to vector instructions in TCG. And that is quite nice. We want to use vector instructions as much as possible. However, the problem here is that our input code is not so easily vectorizable in all cases. So here I have a C function, a hexagon function for a vectorized add of 8 bytes. And it takes in 2 input registers, it loops over the bytes, and we'll go over this briefly. So it extracts the bytes, performs the addition, and then it writes back the result by ORing it together with the result and then returning the destination register. Now, the problem here is that this is not so easily vectorizable due to the shifts and masks and all of this stuff that's going on in the for loop. So our idea here is to write a simple pass to transform these types of functions to something that instead operates on arrays, as you can see here on the right, and then just ORs the result together at the end. And if we do this, we would then get our desired result here. So we would get a few loads and bit casts, and then the vectorized add instruction, which is what we're after. So at this point, I want to start kind of wrapping up the presentation. So first, I want to go through a demo. So I'm going to switch to my terminal, which I have open here, which I hope you can see. Now, on the left-hand side here, I have some input C code where we can type out our instructions. And on the right-hand side is the generated TCG code. So we can start just typing away here. We can type for instance, if we want to create an add function, we can just create something like this that returns A plus B. And if we run our translator, which I've now bound to my keyboard to F5, we end up with some TCG code here on the right, which you've seen before probably, or you have seen it during the talk. We can create more complex examples as well. So for instance, an instruction that computes the absolute value. We can do it simply with a ternary expression like this. And in the output, we end up with a call to TCG gen abs, you can see here, which is precisely what we're looking for, and this has to do with LLVM being clever and figuring out that this ternary expression is actually an absolute value. I can also briefly show you, let's see here. I don't want to type this out because I'm probably going to mistype it. So I have an example of a branch. So we have a function that takes in some input and branches depending on that input. And if we look at our output here, we don't have super much time to go through it thoroughly, but we see a conditional branch here. We branch to either L0 or we branch to L1 down here. And these are our 2 basic blocks in this function. So we have a basic block here and we have a basic block down here. Now, there are a lot of cool examples that I could show you, but we're running a bit low on time. So I'm going to switch back to the slides and start wrapping up the presentation. So I want to provide a brief summary of our IR to IR translator. So hopefully by combining LLVM and QEMU, we can simplify the development of fast and jitting emulators. And hopefully then all that you really need is to have a set of, say, C functions that describe your instruction semantics, and you are pretty much like halfway there in terms of a QEMU front end, and you can start creating your own emulator that way. So that is the end goal, and I think we're well on our way. So currently we emit TCG code for 1500 instructions, which is really good. So this is the same amount as our Flex and Bison parser. Currently the code we output isn't as efficient, and there are a few reasons for this that we're digging into. So we're looking currently at vectorization, as I mentioned, and also at the handling of constant expressions, which we didn't talk about here, but it's pretty interesting. And last but not least, we plan to open source all of this work in collaboration with Qualcomm, so it can hopefully be useful to the broader community. Now I just want to wrap up by extending two thank yous. So I want to say thank you to the Qualcomm Innovation Center, not only for sponsoring this talk, or not talk, but project, but also for helping us throughout development. And I want to thank Taylor Simpson and Brian Kane in particular. And lastly, I just want to extend a big thank you to you all for listening, and I'm looking forward to your questions in the Q&A. Thank you.
Okay, thank you guys for the interesting talk. So there's a question in Q&A. Some people are asking, suppose we had C/IR, so it's an intermediate format using Clang for C. If we had that, would that be easier to work than going all the way down to IR and later to lift back to C that is emitting TCG?
That is an interesting question, and I'm not 100% sure. I'm not super familiar with C/IR myself.
Yeah, I think it's closer to an IST, I guess. Yeah, I think that LLVM IR maps quite well to TinyCode because after all they are both IRs, and I think LLVM IR is the sweet spot to make this kind of translation. Even the presence, all the transformations that we can make, such as the vectorizer, I don't think that would be easily doable on something higher level. So I would say that LLVM IR is the right spot to be for this.
Okay, thank you. So there's another question. Someone asks about the liveness analysis, and in particular, why is that important? Was it because you have to free temporaries in TCG?
Yes, precisely. So we need to free temporaries in TCG. And before we had the liveness analysis pass, we just created all of our variables when we encountered them in the IR, and then we freed everything at the end of the function. And this is not really a good approach when you want to think about optimizing the code you output, and also in terms of kind of helping QEMU optimizing the TCG we generate. So it's firstly to free everything as soon as possible, and secondly to choose the correct type between TCG temporary and a TCG temporary local.
Okay. Thanks.
Yeah, actually, I just would like to add one thing. Actually, QEMU has its own liveness analysis that it uses to perform register allocation and things like that. But the thing is that if we were not to free variables as soon as possible, we actually ended up using so many variables that it will exceed the limit for certain very long instructions. So it's a matter of efficiency in translation, but not necessarily at runtime, and also elegance, let's say, and doing our implementation that makes sense and not just creating an infinite number of variables. And obviously choosing between local and temporaries, on the other hand, that affects performance significantly, because basically local variables whose scope is the whole function, they are way less prone to optimization for how QEMU is designed.
I see. Thank you, guys. So we have a couple of more minutes for questions. I don't see any other questions popping up. I do have a couple of questions though. So you guys have told us at the beginning of the talk that one of the reasons you ended up using, let's say, compiler techniques for building an emulator is for performance. Can you give us a little bit more insight into that? Do you have performance comparison? How faster is this approach compared to others?
Okay, that is a very interesting question, and we do have some performance data. I actually prepared a performance demo as well. Do we have time to show that? I'm not sure.
It's 1 minute and a half. I see it from the timer.
Oh,
yeah, let's give it a shot.
Let's give a quick. Okay, can give it a quick example. So I have another terminal open here where we have a bunch of different files. So we have QEMU-Hexagon version 2 and version 1, and the first one here is the pseudocode, and the second is the LLVM IR, and then we also have Hexagon Sim here, up here, which is an interpreting emulator. So we can run the interpreting emulator. I have a demo program set up here as well, which is a simple kind of water simulation-ish using cellular automata. But if we run it, we can see that it runs pretty slowly. It's running, but it's slow. And if we, for instance, try running instead the LLVM IR based version, we can see that it performs a lot faster. Now, this is of course a pretty silly example, but when we have done more extensive tests, it's more, we can see a performance difference of maybe 26 times roughly. So our TCG-based approach is 26 times faster than the interpreted emulator.
Yeah, actually, we have to add that Hexagon Sim does a bit more. It also simulates caches and things like this. But the thing is, if you compare the approach of interpreters and let's say having a dynamic binary translator, the order of magnitude in performance that you get is, for sure, in the order of magnitude. And but yeah, apart from that, I also want to stress that one of the core benefits, it's not just the performance, but also how easy it is to add support to a new emulator. It's also maybe mainly an engineering benefit. So you don't need to be able to write a tiny code generator. You don't need to understand all of that. You can just have people write C functions and you get an emulator. And that's, I think, it's the core of our work. And I think that's why it's interesting.
Thank you, Ale. I have to interrupt you now. We are running out of time for questions. But thank you, guys. It was very interesting.
Thank you.